Chairman. This is Johann Sebastian Bach. The music you're listening to at the moment is a composition of Bach's called a fugue. Now, a fugue is a piece of music that is about itself. There is a theme called the subject, which you heard right at the outset. That theme appears throughout in multiple, separate, interleading lines. In the case of this piece, there are 4 of them, and this is a very complicated fugue. Right at the outset, you heard the subject. As it's going along, you hear the subject squished by a factor of 2, the notes sounding only half as long. There are other instances of the subject that are twice as long, stretched out by a factor of 2. And all 3 of those possibilities are occurring right now simultaneously, inverted, upside down, with the note positions reversed. And as we get to the latter part of this fairly short piece, all of these ideas start tumbling over one another, stacking up, overlapping, a technique that lends excitement and dynamism and increasing tension to the fabric of the music. And all of this is presented in an absolutely precise, rigorous, logical fashion, progressing through the voices in time and in pitch. In every regard, this is musical science. And yet, from this seemingly cold and calculating way of composing a piece of music emerges breathtaking art. Isaac Newton published his laws of motion and his law of universal gravitation when Bach was 2. And it was a signal moment in the scientific revolution. For the first time, we could predict. We had mathematical formulas that allowed us to be predictive and understand what would happen in the future. At the heart of the reason we can send a little spacecraft 3.5 billion miles across space and put it within 20 miles of where it needs to be to carry out its mission objective above the surface of Pluto. At the heart of that are Newton's laws. And that's tempting to make us think that if we are then armed with the right ideas and the right sets of mathematical equations to express those ideas, well, perhaps we could be fully predictive, fully understand our universe, acquire the so-called theory of everything. The idea that we could do that changed a little bit in the 20th century. Now, as a kid, this was my mental model of the hydrogen atom, or the proton down at the center, a little ball there, and then the red electron, sort of like a little planet orbiting the miniature sun at the center. We know now that this is a completely erroneous way of interpreting the atom. And, by the way, this is more like what an atom actually looks like. And, using mathematics, perhaps a little less accessible than Newton's equation. This is the formalism of quantum mechanics, the discipline of physics that underlies our modern understanding of the universe. In the quantum formulation, we don't know where the electron is. We have merely these beautiful colored areas that show us where it might be and where it might be headed. We don't know where it is, and even more profoundly, quantum mechanics tells us we cannot know where it is. It is as if there's an innate fuzziness, an innate uncertainty programmed into the very fabric of the cosmos. At about the same time that quantum was developed, we also came to the realization that mathematics itself, the language of science, mathematics is fundamentally limited in its explanatory power, a concept known as incompleteness that was advanced first in 1930. Any set of mathematical formalisms that we put forward can be proven to be inadequate to fully describe the system to which they belong. Mathematics is fundamentally incomplete. This has led no less a mind than Stephen Hawking to conclude that, in fact, we never will reach a theory of everything. In a beautiful lecture, which you can find online from 2002, Hawking explains the reasoning. When we try to do astronomy, when we try to understand the universe, we're not outside looking in, poking it and trying to understand it. We're inside it. We're part of the system to which we belong and to which we're trying to understand. That will prevent us ever from fully comprehending everything that is out there. The quest for knowledge will be eternal. That's a concept that I actually rather like. Now, I keep these ideas in mind every time I do science. And to explain why, I'll put up just one graph for you here. This is a set of observations of the sun made at Lowell Observatory over the past 22 years. Every one of those yellow dots is an observation of the sun that we've taken. What we're trying to do is understand how the sun changes over years and decades. We're studying things like sunspots, flares, prominences, coronal mass ejections. These things have practical impacts on Earth and the space environment around Earth. So we'd like to understand how our star behaves. Every time I work with a data set like this, I worry about two things. First of all, there's analyzing the data. Every one of those yellow points has error. It has uncertainty, fuzziness, and we need to understand the error in our data in order to interpret them correctly and in order not to over-interpret them. But then I also try to take a step up one level and analyze myself analyzing the data. It's very much like listening to a fugue, and it's tricky to do. I ask myself, to what extent have I been absolutely scientific in this interpretation? How much have I been completely rigorous, completely precise, assembling a logical, defensible set of statements to a conclusion? But to what extent have I also been artistic? Maybe there were 2 or 3 mathematical tools I could have used to prepare the data for analysis or to make one interpretation or another. Why did I pick one or the other? Did I make a judgment call? Did I just go with my gut? Did I use that brushstroke instead of that one? Because this one just feels a little better. There's an element of that every time we practice science, and perhaps most subtly, we all have our internal preferences. We have biases. I absolutely believe in unconscious bias, those inclinations we have that we may not even be aware of. To what extent have I coded myself into that plot? Well, that's why scientists review their own work. This plot, which has been submitted to a professional journal, cannot appear until it has been reviewed and evaluated by another professional astronomer, standard practice in science. And in fact, I didn't even make that plot myself. I'm so close to those data, I thought the best thing to do would be to fire them off to a collaborator, a really bright graduate student at the High Altitude Observatory in Boulder, Colorado. And he produced much more of a blind experiment. In the end, I think what we've got here is actually a really nice scientific result with good grist for future studies, and also a rather beautiful thing, that gentle undulation going back and forth over the decades, revealing the hidden patterns present in our star. So this deep connection between science and art, I don't think has ever been expressed better than by the old master himself, Bach. So in the last decade of his life, Bach composed a number of monumental works, summative works of his career. One of them was an 80-minute cycle of some 20 different fugues. The piece you heard at the start of his talk was one of those. The manuscript you see here on this slide is the last page of the last fugue in that cycle. And over that 80 minutes, a single theme is presented, explored exhaustively in every possible different way, in units and in subunits. It is the pinnacle of musical science, and yet Bach pointedly titled this work, The Art of Fugue. Now, even if you don't read music, you might look at the second line of that manuscript and you'll see how the notes kind of thin out and trail off right in the middle of the staff there and sort of trail off into nothing. And it looks like it just kind of wanders away into silence. And indeed, that's exactly what happens. This fugue is incomplete. And hidden in that fugue, even if you do read music, are something that's considerably harder to see. I'll just put little red boxes around them, 4 notes hiding in there. Let me pull them out into notation that's maybe a little easier to read, and I'll just play that for you. It's very short. Kind of a querulous, unnerving little theme. In music, in key spellings, we give keys names with letters of the alphabet, A through G, right? Key of A through the key of G. Actually, in the German system of key lettering, the system goes through H, not G. So in principle, you could spell anything with musical notes that contain those letters. And in fact, those 4 notes do spell a name. Wow. Bach has made the point for us explicitly. He has coded himself into his own science and art, as perhaps do we all. A little bit of us is always intertwined on those 2 ends of the pivot, science and art, blended forever into these lovely combinations of the eternal and the incomplete. Thank you.